start with this penultimate lecture. So until now we have defined AdS-CFT in various types of scenarios, but today we're going to look for applications to the real world. So specifically today, this lecture to applications to condensed matter, and the last lecture applications to particle physics. Okay, so the generic name for application to condensed matter is AdS-CMT, condensed matter theory. And generically, this is a phenomenological approach, by which we mean that there's no known way to derive the duality, because there's no known way to describe a large N gauge theory, to describe a condensed matter system via a large N gauge theory. That's basically the reason. So because of that, all of the models that we're considering are basically phenomenological in nature. So we derive some model, we define some model, and then we see if the physics that is obtained is something that we want to describe. So this would be a bottom-up approach. So we define, let's say we want we want some conformal field theory. So we want some conformal description for a system that we're interested in, and then we want some other type of properties. So then we will construct a gravitational theory that has the properties such that under the holographic map it would give rise to such such properties. Now it's important to realize that we are assuming that holography still holds, and moreover assuming that the holographic map still holds, even though in this case we don't have a derivation. This is contrary to the so-called top-down approach, where we would derive some duality from string theory like we did in the previous lectures. But the problem with top-down is that we're very much restricted in the choices that we have. So there are, finitely many known dualities, yeah, it's hard to find some condensed matter system for which this is appropriate. But nevertheless, we sometimes use them using that kind of terminology of universality, saying that some particular variable seems to, some particular observable seems to give the right result, so, well, we're happy. Yeah. You will define a gravitational theory in such a way that it via the holographic map, it describes the physics that we want. Well, I mean, people have considered also non-conformally invariant theories, but it's complication on top of a complication. So usually people don't take that too seriously. So I mean, it's one thing if you have a top-down approach, then you know at least the rules of the game a little bit. But in here, you have to assume a lot of things. You have to assume holography exists, and moreover, the holographic map exists. So at least for AdS, we have some arguments for that. We have some arguments that the finite time it takes for light to reach the boundary, the fact that the AdS symmetry is conformal symmetry. So yeah, if we go beyond that, you know, everything is completely out. Yeah. The top-down approach requires you to already know the duality. So we will see later, I guess, or maybe I didn't see it, but didn't say it. But so people in condensed matter are mostly interested in 2+1 dimensions. That's where, you know, non-trivial, interesting things happen. And so just like AdS-5 crosses 5 versus n equal 4 span Mills was a kind of toy model for all 4-dimensional physics, there's a model called ABJM model, which is a Chern-Simons gauge theory with gauge group SUN cross SUN that corresponds to AdS-4 cross CP3 string theory, and that's also taken to be some sort of toy model for 3-dimensional physics. So people apply that to a lot of systems, but it's a toy model, is, you know. Okay. Yeah, so I should say, so yeah, actually the first example slightly contradicts me. So AdS is a relativistic, corresponds to a relativistic theory. Conformal field theory is kind of relativistic from that point of view. But there's also, we'll be interested also here in non-relativistic versions of that. So the first example then is for gravity dual of so-called Lifshitz scaling, which is some non-relativistic behavior that is common in many condensed matter systems, where there's a scaling, but, so like in conformal field theory, there's a scaling symmetry, but the scaling symmetry scales differently space and time. Namely, it scales time with a power z, whereas space is scaled with just power 1. And you might wonder what that means. So, well, you can write a model example for that, which is Lagrangian integral in 2+1 dimensions. No, sorry. Yeah, Lagrangian in 2+1 dimensions. No integral over t. dt phi squared plus so or minus k del squared phi squared, right? Instead of del phi squared is del squared phi squared. So this has obviously a scaling with z equal to 2. So the phenomenological gravity dual in this case is just a non-relativistic version of AdS that has this scaling. So AdS in Poincare coordinates, let's say. So ds squared d plus 1, well, we have our overall scale r squared. And then here I would write, so for AdS, I would write this. Right? Everything for AdS, the whole dt, dx squared, and du squared will all be divided by u squared. But for the non-relativistic scaling, I would put this power z. Okay. And this has this scaling, and then of course also, now for the gravity dual, I also have lambda u. And we can write down the killing vector or generator of this scaling symmetry. And well, the D is minus I, the usual thing. Then I would have written normally T dt plus xi dxi plus u du. This would be the scaling operator when I scale all the coordinates the same way. But now I have also a power multiplied by a factor of z in here. And yeah, then as usual, Mij, the spatial rotation operators are again with minus I, then xi dj minus xj di. And the momentum is minus I di, and Hamiltonian is minus I dt. Yeah, and then once you have these operators, you know, you can just start commuting them, and you obtain the algebra written on page 180. Yeah, so for this part, for the part of just Mij, Pi, and H is the usual one, but once I include D, I get a different algebra. So D with H is Z dt, and what else? Yeah, just this one. So D with H is IZH. Right. Okay, and so the background must be a solution to some gauge theory, and there's to some gravity theory, excuse me. So there are 2 points of view. You can either consider relativistic theories, relativistic actions, so relativistic gravity theory, or non-relativistic gravity theory. And in the latter, one has the Rojava gravity example. If you don't know, I will not explain this, but it's some non-relativistic version of gravity. So in the relativistic gravity case, what would happen, you still need to break something, so what you would break is gauge invariance, so by adding. So in this case, it's r minus 2 lambda for AdS gravity, and then minus a quarter f mu squared for a Maxwell term, but actually you break the Maxwell invariance with a mass term. So the mass term gives the non-relativistic property. So this algebra in here is called the Lifshitz algebra. Corresponding to Lifshitz scaling. But you can consider larger algebras. You can consider the so-called conformal Galilean algebra. So usual conformal algebra, as we said, is relativistic, but the Poincaré part of the conformal group in the non-relativistic case reduces to the Galilean group or algebra. And so the conformal Galilean algebra is some sort of non-relativistic version of that. So what is added here is a conserved rest mass or particle number. So in a relativistic theory, the particle number is not conserved because you can create particle-antiparticle pairs. But in a non-relativistic theory, particle number is conserved. So, and then you also have these Galilean boosts. So in here, I only considered rotations, but we also consider Galilean version of boosts, where you know, x goes to x minus vt, and time is unchanged. And in the particular case, so for the particular case of z equal to 2, and the example was that for z equal to 2 was that field theory I wrote over there with del squared phi squared. Oh, sorry. The particular case of z equal to 2, we have an extra generator. Oh, and we have an extra generator, C, which is the equivalent of the special conformal transformations for the relativistic case. Now there's a special conformal non-relativistic generator. And in that case, this would be the Schrödinger algebra, where the names comes from the fact that this is the invariance algebra of the Schrödinger equation of a free particle. So in this case, the gravity dual is somewhat non-trivial. It's found by adding 2 coordinates instead of just 1. So we have our gravity dual over there, but I have a different color. So then I would add another coordinate that only appears another coordinate psi that only appears in the off-diagonal term dt d psi. And because of that, this is not time reverse invariant, because if I change the direction of time, I get a minus sign in here. And it's actually also conformal to the PP wave, because if I take out a factor of, so let me write it here. So it's conformal to a PP wave. If I take out the factor of 1 over u squared, this becomes, so minus dt u to the 2 minus 2z, minus dt squared, u to the 2 minus 2z squared, plus, well, dx squared plus du squared, but then plus 2 dt d psi, and you note that this is like the u and v, or x plus x minus of the PP wave. And so let me call this x plus and then this x minus. Then I have here dx plus squared, so this is like the harmonic function h. Okay, so this is really conformal to a PP wave. And it's invariant under the Lifshitz algebra, Lifshitz scaling, complemented with the scaling of u and complementing with the scaling of psi. Okay. And so the generator in this case gets also So it's this, but gets also an extra factor corresponding to this scaling, so plus 2 minus z xi d xi. All right. And, well, you can, oh yeah, and in this case, there's also an extra Galilean boost, xi I, ki. So, Galilean boost. Yeah, sorry, I've written it here. So there's this Galilean boost that would have corresponded to a generator ki, right? So, yeah, I mean, I can write this ki like there, so minus I, xi d xi minus tdi. So for the Schrödinger algebra, then we have extra n, ki, and also extra c. And again, you commute the generators defined this way, and you find the symmetry algebra written on page 182. Yeah, and so, sorry, so you find the conformal Galilean algebra for z different than 2, and for z equal to 2 with the extra generator c, you find the Schrödinger algebra. So this is now becoming very long. Obviously, I will not write this, but the idea is simple. You just, as you say, as I said, I defined and this was, of course, minus I. Minus I d xi, and then you just commute the generators and find the algebra. So there's nothing fancy in here. So so this was all phenomenological, right? I basically wanted to have Lifshitz scaling, and so this was the first case. Then I added conservation of rest mass and Galilean boost to have the conformal algebra. And for z equal to 2, I just observed that there's an extra symmetry generator C, and I get the Schrödinger algebra. But these are not, these were phenomenological, not obtained from anything. However, I just want to point out that the Galilean algebra is obtained, for instance, by a set of steps, a procedure called null-Melvin twist that I will not describe, and which results, you start with AdS-5 crosses S5, and then with a temperature T, and then you get this complicated metric on top of page 183, and you find that it has the conformal Galilean algebra. And also it contains for z equal to 2 the case of Schrödinger. Okay. So this was the first application, the application to non-relativistic, to various non-relativistic algebras that can appear in condensed matter. But now let's turn and look to things a little bit more common in condensed matter. So one of the such things that are very useful are the retarded Green's functions. So I call this G retarded, OA, OB. And that's basically just the commutator of the operators with retarded means I put a Heaviside function for time. So O, X and T, OA, with OB 0, 0, with theta of T. And so this is in X space, then the most common applications are in momentum space, so then you take the Fourier transform on this. But the retarded fact is that is due to the Heaviside function of T. And why is this important? Because what we do in condensed matter, we do usually linear response theory. We perturb the condensed matter system with something, and then we see what happens to it. So, and then it's easy to show that the variation of the VEV of the operator A is the retarded Green's function OA of B times this variation that you considered for the field coupling to operator B. Okay. And the fact that it's retarded, then when you consider it in momentum space, means some conditions on the possible behavior of the retarded function. It's analytic in the complex frequency plane, in the upper half plane, and goes to 0 at infinity. And these conditions imply generically, so these two conditions, this is just complex function theory, this condition implies generically that you can write the retarded function as an integral. So gr of z in the complex plane, you write it as an integral over a closed contour of gr, so over 2 pi, gr over z minus zeta. Or zeta minus z, sorry. Sine. And this in turn gives the so-called Kramers-Kronig relations, which are also relations in general complex function theory, but in particular applied to the retarding Green's function, which relate the real and the imaginary parts of it via complex integration as written there. So the real part it's the integral of the imaginary part, omega minus omega prime, and the same thing, so, well, the principal part of the integral, and the omega over pi, and the imaginary part with a minus sign, the real part here. And then one can also consider the omega goes to 0 limit of this. And in the omega goes to 0 limit, the so the corresponding object for the retarded Green's function, it's a static thermodynamic susceptibility. Static because omega goes to 0, but it's a thermodynamic susceptibility. And because it's a real part, so because this is a real object, it's related by the first Kramers-Kronig relation with the imaginary part. Right? Yeah, sorry, here is my omega prime minus omega, so I put omega to 0. And so this is the principal part of the integral of the imaginary part. But the point here is that this is then equal to, so like we've seen in here that the retarded Green's function was the response in linear response theory to a perturbation in the field phi b, resulting in VEV OA, right? So this can be thought of as the derivative of this with respect to the field phi b. Yeah, and one can define, I don't think I need to go into all this detail, but one can define the spectral function as the imaginary part, and the advanced Green's functions. Advanced Green's function would be where I consider, instead of theta of t, theta minus t. This would be advanced Green's function. And then the spectral function would be obtained from the difference of the retarded and advanced Green's functions. Yeah, okay, some formulas which I don't really need to describe. Okay, so with all of this, the most common application is for transport. So we have some type of quantity. Usually we're considering electric charge or heat that is being transported across the system. So that's what we take as our perturbation. Okay, so for transport then we have the so-called Kubo formulas. So these are generic formulas, but the original Kubo formula was for the electric conductivity, so that's what I will first describe. So the let's say 4 sigma electric conductivity. So in this case, the source is an electric field. We input an electric field to the material, and then a current will result, right? So that's these are our 2 objects. So considering the gauge A0 equal to 0, then the electric field in the direction J is F0J, as dT-AJ. And moreover, I said I want to consider a perturbation, so a perturbation in the field, so perturbation in the gauge field, all right? And further, I want to consider momentum space. So here I wrote things without specifying it, but in the slides I put momentum space because that's the usual way of describing this. So then this becomes minus I omega, or I omega, yeah, minus I omega. delta AG, AJ of omega. Okay. And then the response is the VEV of the electric current, let's say in the x direction. So this, on one hand, is by definition sigma times the electric current, Ex. But then we also saw that this would be the retarded Green's function, right? Oh, sorry. So, and then sigma Ex is equal to minus I omega sigma delta AJ of omega. But then, on the other hand, from the general theory, this would be the retarded Green's function Jx. So again, Jx, because in here I denote the operators. So the operator that couples to phi in this, so OB is the operator that couples to phi b. So the operator that couples to AJ is still Jx. So J times, so GR Jx times delta AJ of omega. So we get that sigma is I J Jx R over omega. Right? There I wrote the relation in the original form of Kubo, where he was mostly interested in the real part of the conductivity at zero frequency, so the real DC conductivity. But the formula, as you see, is valid in general, right? So I can write this as omega and k, and IGX will give some other complex value. So if I want to put the real part in here, I get minus the imaginary part in here. And then if I want, I can put also the omega goes to zero limit. Then the next interesting thing is the shear conductivity. Sorry, the shear viscosity. So the shear viscosity appears in a relativistic theory by the expansion of the energy momentum tensor. So, so I don't know if you're familiar with this, but so you're familiar with the Euler equation and the generalization of the Navier-Stokes equations in the case of the non-relativistic theory. But in a general relativistic theory, what happens is, so relativistic theory, what those equations amount to is simply, well, covariant. The covariant version, the covariant conservation of the energy momentum tensor. And then, so if you know, if you can expand this for a perfect you can expand this for a fluid, and then you would get the Euler equation. So in the non-relativistic limit, you would get the Euler equation, and then the corrections would give Navier-Stokes. This is an interesting exercise that I think everybody should do at some point. It's very simple. So what does that mean? So in this relativistic theory, the general prescription is hydrodynamics, the description of fluids, is a long-range description of some generically quantum theory. And the Euler fluid, the ideal fluid, is simply the 0th order approximation to this expansion. So the expansion for the fluid, so if I have some fluid, it's defined by some density, pressure, and some velocity, right? Some velocity field. And so when I write a generic, completely generic energy momentum tensor, can be thought of as an expansion in derivatives of u mu. So expansion in derivatives of u mu. And so the 0th order term, so 0th order term is Euler, and first order is Navier-Stokes. But in principle, I can continue the expansion to any order I want. So the Euler case, it's known, it's rho u mu u nu plus P times the projector, which is g mu nu plus u mu u nu. You note that this is a projector because it's a projector on the transverse direction to u mu, because multiplying it with u mu, I get 0. So this is Euler. And then Navier-Stokes is the second order. I mean, first non-trivial order. Is written as 2 eta sigma mu nu plus minus zeta theta times this p mu nu. So this was called p mu nu. The projector, p mu nu u mu is 0. The transverse direction to the velocity. And so eta is called shear viscosity. And zeta is called bulk viscosity. So those are two viscous terms, which means they, in the usual interpretation, there are terms that oppose, due to friction, that oppose the motion. But in this simple expansion of the energy momentum tensor in derivatives of the velocity, these are simply coefficients of the possible expansion terms of d mu u nu. So this is a 2 tensor, right? The derivative of the velocity is a 2 tensor. And so I can expand it in, as usual, as we did, for instance, in string theory, expand it into a symmetric traceless part, an antisymmetric part, and a trace. And the symmetric traceless part, is called omega mu nu. It's called, sorry, sigma mu nu. Symmetric traceless. Omega mu nu is the antisymmetric part, and theta is the trace. Okay? And I've written there a little bit with formulas, all of this, but it's clear. Okay? Good. So now So now let me consider the expansion of a fluid at rest. Expansion of a fluid at rest. So expansion in perturbations. Right? And you see in 0th order, I have the perturbation of the metric, right? That will be multiplied with the pressure, right? And so, yeah, I should say in perturbations of G mu nu, perturbations of the metric. So in 0th order, I have the perturbation of G mu nu in here. That multiplies the metric. And then in 1st order, I look over there and I see that from sigma mu nu, I find that there's also a term proportional to the perturbation of the metric. So, I mean, this is a calculation one can do. And one finds that the perturbation of the xy component is phxy from this term, right? And then there's a perturbation with derivatives on of the metric. And the one that we're interested in is time derivative. Just like over there, we're interested in time derivatives because eventually we'll be interested in going to momentum space and we'll be interested in frequency. So one finds the time derivative dt hxy for txy, and the coefficient here is eta, right? And then, of course, these are, as I said, only the 1st order terms. First, they are linearized, so there are also nonlinear terms with hxy squared and so on. And there are also higher order terms in the derivatives of acting on velocity and so on. And so these will give higher order terms with derivatives of hxy. But here I'm interested only in the linearized and 1st order derivatives in time. And then going to omega space, right? This gives nothing, or rather I should say, well, this would give a dependence on xxy, but hxy, but would be a real part. And then in here, I would get from this term minus I omega hxy omega. So now we do the same as we did for electric conductivity. We compare that with the general relation, which is the variation of so the variation of so we can say it like this. So the variation of T8xy with respect to the hxy is gr txy. So note also that hxy is the thing that couples to txy, right? Because T mu nu is minus 2 over square root minus g, derivative of action with respect to g mu nu, right? So I have this coupling. So this couples to the variation of g mu nu in the action. Okay, so this is gr hxy. So, but then from this we get that is also, oh sorry, important, eta, minus I omega eta, or that eta is I gr txy over omega. And again, this is so this is a shear formula for the shear viscosity. And again, we could also consider the zero component, then and the real part. So the real part of eta 0, 0 is minus imaginary part gr 0, 0. I mean omega 0 over omega in the limit omega goes to 0. So that's kind of the more standard one, the DC one. Okay. So the next interesting question is, how do we do AdS-CFT in Minkowski space? So this is an important question because most of the things that we said were in Euclidean signature. But in Minkowski space, in Lorentzian signature, we said a few things about correlation functions at the beginning, but now let's say also some things about retarded Green's functions. Okay, so this was found by Son and Starinets in 2002. So the application here is Minkowski space and finite temperature. That means black holes. So the observation of Son and Starinets was that if I can consider so if I can consider that the supergravity on-shell action is written as an integral of a quadratic form of the boundary source, and I define the thing in the middle as F, then, so, yeah, that depends on the boundary, on the radial direction Z. Then the prescription for the retarded Green's function is just -2 this F considered at the boundary. Now, this can be made more precise in an equivalent formulation. So, if one considers the renormalized action, so renormalized action is the on-shell action plus the counter term, plus S counter term at the boundary. Then the one-point function is the variation of the the variation of the subtracted action, if you remember. the variation of the subtracted action with respect to the boundary source, but then multiplied with a factor of square root of the metric, and then taking z, or epsilon, as I called it then, to 0, to the boundary. So limit z goes to 0. Here I had the subtracted action varied with respect to phi 0 z, and here I had some square root minus gamma. Well, yeah, 1 over square root minus gamma, and then this r over z to the delta. Okay. And the counter term that we found was of the form written there. So S counter term, or boundary, was the integral of phi squared with a coefficient delta minus d over 2r. And phi of z was expanded. Phi of z has in it 2 independent objects, one that corresponded to the source, one that corresponded to operator expectation values, or states. So this is z over r. The z over r, just to have dimensionless things. to d minus delta phi 0 plus z over r to the delta phi to delta minus d. So both of these behaviors came with subleading terms, but the leading terms correspond to the source and operator vev respectively. So these are things that we've considered before, and then again things that we've considered before. We get that the 1-point function is equal to minus 2 delta minus d over r times phi 2 delta minus d. And now finally I do the I apply this for the Green's function, which was linear response, so the variation of OA with respect to phi b 0. And so now is minus 2 delta a minus d r delta phi a to delta minus d with respect to phi b 0. Okay, so except for this overall factor is what we've described before in holographic renormalization. So it's the variation of the operator vev term in the expansion of phi with respect to the 0th order or source term in the expansion. And here the only thing that's happening is, this is a bit more general, is OA with respect to OB varied. Okay. So I've written for you the Kubo formulas for the electric conductivity and the shear viscosity. But for electric transport, if I have non-zero charge density, electric and heat transport mix, and we have a mixing matrix. So x refers to the x direction, because you have to remember also the the matrices, the conductivities are also matrices. So for instance, I write Jij is sigma ij ej, right? And sigma xx is the regular conductivity, sigma xy is the whole conductivity. So these are also conductivities in the space directions, but matrix conductivities in the space direction, but now I consider just for xx. And then they mix like this. So alpha t, kappa bar t, with respect to Ex. So the normal one is Jx sigma times Ex. There's also the heat conductivity, which is the response of heat with respect to gradient of temperature divided by temperature. Yeah, kappa bar, I always forget how it's related. So there are two conductivities, kappa bar and kappa, and they're related by something like this. I don't remember exactly. As matrices, something like this, I believe. Anyway, so the conductivity kappa bar is the one defined in this 2x2 matrix. And then similarly, of course, I will get Kubo formulas for all possible ones, so all possible coefficients. So alpha t, this guy is the response of Jx to the gradient of the temperature. So this is Ig, or vice versa, the response of heat to electric current. So this is Ig Qx Jx R of omega. And kappa bar T is GR Qx Qx over omega. Okay, so now one of the most consequential relations in these applications to the real world, not just condensed matter, but also to plasma, is the application for calculating shear viscosity over entropy density. So it turns out that we can calculate this easily from dual black holes. So we said that this was for Minkowski space at finite temperature. This was the prescription to calculate the retarded Green's function. And so basically, I will calculate the retarded Green's function from this prescription at finite temperature. And then I will use the Kubo formulas that relate the transport coefficients. So yeah, just to write, we also had IGR Jx of omega, and eta was IGR Txy of omega. So with the prescription of Stone-Starry nets, we can calculate the various retardant Green's functions, and then from them the transport coefficients listed here. So how do we calculate the retardant Green's function corresponding to Txy. So for finite temperature quantum field theory, we know that we have the Witten metric, or AdS black hole. But we also know that after a change of coordinates, it becomes the same as the near horizon, near extremal D3 brane D3 brane solution. And so that is ds squared is r0 squared over r squared u minus f of u dt squared plus dx3 squared plus r squared du squared over u squared f of u over 4. Then f of u is 1 minus u squared. So then we consider perturbations, and if we are interested in eta, therefore gr txy txy, we have to consider hxy perturbations. So hxy perturbations. And these are considered, so remembering the relation, so one way was in this way to calculate them, the other way was in this way, but in either case, we have to consider the perturbation throughout the space. So we have to consider the perturbation not as a function only of the field theory coordinates x, but also as a function of the radial coordinate y. So then we have the boundary one, which is ikx minus I omega t. Yeah, I guess I called it q, not k. Q. But then we also have this phi q of u over u with a normalization r0 squared over r squared. So in principle, as I said, we would need to calculate the full solution at, so at least if I apply this formula, I would need to calculate the full exact solution. And then in the full exact solution, this would be a function of this, but only the full exact solution, if you remember. In the perturbation near the boundary, these two things are independent. They are the coefficients corresponding to operator vevs and to sources. So this is hard. It's possible sometimes, but it's hard. But instead, there's a simpler way which takes into account this first formula of Son and Starinets. So it's based on the fact that the calculation at the horizon is approximately equal to the calculation at the boundary, and at the horizon we can calculate the form of this. So at the horizon, this becomes phi 0, 1 minus u to plus or minus I omega over 4 pi t. So this is just from solving the Einstein's equations near the horizon. And selecting the solutions with plus, which are incoming or infalling inside the horizon, not outgoing. And then the retarded Green's function is just minus 2 times this function that multiplies the two phi zeros. Okay, and so we have here a phi 0 for each phi q, right? So if I write the quadratic action, it will have two such hxy's, therefore it will have two phi q's, and therefore it will have two phi zeros, okay? So I take out the two phi zeros, and whatever is left is the retarded Green's function. Yeah, and then from the Green's function, I just divide by omega, take the imaginary part, divide by omega, and I get a result. And one gets that eta is pi over 8 n squared t cubed. Okay. And then we have already calculated that the entropy density was also pi squared over 2 n squared t cubed. So for the entropy density, n squared t cubed was just from general thinking. So, you know, it has n squared degrees of freedom for the adjoint matrices, and t cubed is the scaling of the entropy density of conformal theory. But then by taking the ratio of these two things, you see the ratio is 1 over 4 pi. So the ratio of the entropy density, the shear viscosity over entropy density of the dual black hole, of the gravity gravity dual solution found by Witten, is eta over S is 1 over 4 pi. But in fact, this was proven to be the case for a very general set of gravity dual black holes. So almost any gravity dual black holes will have this value, except, so the two important assumptions in here was of isotropy and of Einstein-Hilbert action. So people have found that you can get results that are smaller than this for anisotropic solutions and for solutions that involve R-squared corrections to the action. And for a while, this was thought to be a limit and this came under the name of KSS bound. And the reasoning was that, well, you can see almost anything in nature comes very close to this. And in fact, surprisingly, the thing that comes closest is the strongly coupled quark-gluon plasma obtained in high-energy collisions. And that's very close to this 1 over 4 pi. And that's kind of neat because that means you can, it's one of these universality things that plasma can be described very well by the Witten dual, which is actually for n equal 4 spam mills at finite temperature. So for a while, people thought this was a bound, but then there came all of these exceptions, and then you can also take slightly pathological but very normal exception where you take a very large number of free fields that also breaks this. So in fact, it is not a bound, but people have not have not given up on it, so they still hope to find a different bound under some conditions. So, okay, maybe one can find. All right, now let me switch gears and talk about the holographic superconductor. So I told you, let's see, so I told you about non-relativistic systems that have Schrödinger conformal Galilean algebra. I told you about transport. And another thing that is very interesting to us, not sure how interesting it is to condensed matter theories, that's always the question. But is the holographic superconductor, because it refers to a strongly coupled superconductor that is otherwise somewhat difficult to describe. So this was found by Gubser in 2008 and independently in a paper by Hartendahl, Herzog, and Horowitz slightly after that. So, all right. So holographic superconductor. So what are the ingredients for that? Well, this is also, so the strongly coupled systems that people look for are in 2+1 dimensions. So we need some sort of AdS-4 background. And why AdS? Because this appears, the holographic superconductor description is for near a transition point. So there we'll have, near a transition point, we'll have a conformal field theory. And as I said, this corresponds to 2+1 dimensions. So the thing that people look for is high TC superconductors in 2+1 dimensions, which also correspond to non-Fermi liquids. So non-Fermi liquids means they are liquids that do not they do not obey the Fermi liquid theory because basically they are strongly coupled. The Fermi liquid theory is not. And we need to have some charge transport. I mean, superconductor is good because it transports charge. So we need to have correspondingly U1 gauge field, so U1 J mu in here and U1 A mu over there. We need to have temperature. So we need to have a black hole. And we also need to have symmetry breaking. Via the Higgs mechanism. Or, I mean, yeah, in particle physics we call it the Higgs mechanism, but in condensed matter, you know, it's really a relativistic version. It would be a relativistic version of Landau's theory of second-order phase transitions. So symmetry breaking, then that means that there should be some operator that operator Vev that becomes non-zero, and then that's dual to some complex scalar field that has to be charged. So for the Higgs mechanism, has to be charged under U1. And people would like to, and sometimes describe higher order, so P, D, and F wave superconductors with higher angular momentum, L equal 1, 2, 3. But the basic one is L equals 0, so S equal to, so S wave. So that corresponds to this scalar field. In principle, you can consider, let's say, P wave, which is L equal to 1, and that would correspond to having a field of spin 1, so a vector field that couples to an operator that is operator VEV that's non-zero. So the Lagrangian is gravity plus Maxwell plus a complex scalar with a potential. Complex charge scalar with a potential. Now, in the case of no potential, one can find, and that's an important thing that I think I have not said until now, that there's the so-called BF bound, Breitenloner-Friedman bound, which says that the mass squared of the field has to be greater or equal than a negative thing in AdS. That sounds counterintuitive, but the point is in AdS, because of the curvature, so like in flat space, you think of what happens to the field at infinity. Is it consistent? And in flat space, the consistency implies the m squared is positive. But in AdS, implies that m squared is only greater than some negative number. So it can be still negative, slightly negative. So, yeah, so for d equal to 3, which is our case, this would be minus 9/4 r squared. Okay. And then you write a superconducting ansatz. You write, so basically this would be, as we look in here, this would be a black hole that is charged. It has a non-trivial electric field and also has a non-trivial complex scalar field. So, so one writes an ansatz for this, but the important observation I want to make is that from the Lagrangian, if I have a non-trivial scalar, yeah, sorry, I called the scalar psi because I wanted to call a mu, I called A0 phi. So because we have the coupling to the gauge field, basically I have, if I have a mass for the scalar field, this changes to an effective mass that gets multiplied by, gets a contribution from the electric potential, right? So we have an extra term that acts as an effective potential, that an effective mass. So what do we want? Well, we want phi equal to 0. At the horizon, we want phi equal to 0. So actually, this at the horizon is 0. But the thing is, m squared effective, sorry, this is 0. But the BF bound, this was at infinity. And It turns out that m squared effective will be less than 9/4, so it will be unstable at the horizon. Now, sorry, so this will be less than 9/4 r squared at the horizon, so unstable. So that's what we want to find. We want to find that there's an instability that leads to symmetry breaking. That the instability that leads to an operator VEV and leads to symmetry breaking. And the backgrounds that have been used are ADS Reisner Nordstrom, so meaning so black hole in ADS, but also with electric charge. This was in the original model by Gubser. But then Hartnoll, Herzog, and Horowitz consider also the possibility of just having a neutral ADS black hole, and the non-trivial A mu appears from perturbations. But it's easier to understand things, I think, in the description of Gubser, which I will follow here. So then, oh, I still have these things here. Let me erase. So the scalar phi at infinity is coefficient phi 1 plus the coefficient phi 2 over r squared, and the electric potential is mu minus rho over r plus. But it turns out, which is very unusual, that for this special case, both of these phi 1 and phi 2 are normalizable. So both actually correspond to states or VEVs and not to sources. So this leads then to two possible OIs, which are up to a square root 2, these phi i's for i's 1 to 2. And then one solves the equations of motion numerically because they're hard, and one finds that these OIs go like square root 1 minus t over tc. Yeah, tc there should be not t. So tc is approximately 0.118 square root rho. So this is the behavior that you wanted to obtain, right? This is the behavior that appears in, for instance, in Landau's theory of type 2 superconductors, that the type 2 phase transitions, because that means that there is a singularity at Tc, and moreover, the operator VEV becomes 0, so there's no symmetry breaking at Tc. So below Tc, we have a symmetric phase. Above Tc, we have a non-symmetric phase. Right. So I was saying that that there's something odd that we have at the horizon mass less than 9/4 r squared, but but the bound, but the point is that the bound at so the bound at horizon, so the BF bound at the horizon is different one. So I mean, you can understand because the mass is defined as a perturbation. So the mass depends on where you define it, at infinity or at the horizon. And at the horizon, the space is AdS2 cross S2. Okay, and you remember the BF bound was m squared r squared greater or equal minus d squared over 4r squared. So this is AdS d plus 1, so this is 1 now. So minus 1/4 r squared. So this is a stronger bound than at horizon, at the infinity, right? So this is 1/4 of it versus 9/4 at versus wait. No, sorry. Yeah, it's not 1/4. It's yeah, because it's r, but r is also different. So this is r2. And then this becomes, so 1 r2 squared, and then this is minus m squared r squared over 6. In any case, it's much stronger than 9/4 r squared. So, so the point is that the mass at the horizon, the effective mass at the horizon, dropped below the BF bound at infinity, but was still above the BF bound at the horizon. So it was fine. But because it dropped below the BF bound at infinity, it meant that there was an instability happening at infinity, at the horizon, and the scalar field grew, and correspondingly in the field theory, we have the appearance of a non-zero operator VEV. Right? So the operator VEV was non-zero because these psi's were non-zero, and these were non-zero because of the instability at the horizon. Okay. One can consider electric conductivity in here, and one finds, yeah, so a perturbation in AX, and as usual, one finds sigma is the response to the perturbation in AX, and so on, and when one finds this result, that, so one finds that sigma is 0 for omega less than an omega gap. And this omega gap is, roughly speaking, Q times the VEV of O to some power 1 over delta. And omega gap over TC is approximately 8.4. But this matches the experimental data for high TC superconductors. So the point is, if this would have been a usual superconductor, which is weakly coupled, this would have been of order 1. But in these high TC superconductors, this is large, 8 and something. And moreover, in the experimental data for these high TC superconductors gives something close to this. Right. Yeah, and there's another thing that this omega gap in weakly coupled omega gap is 2 EG, and otherwise is different for strongly coupled. for the gap energy in the charge spectrum. But the weird thing is, so this is a puzzle that I don't think has been resolved yet, that in the holography this is still true. So it's strongly coupled, so EG is generically different than omega G over 2, except for scalars corresponding to operators with dimension 1 or 2, in which case it is still true. So for these guys, it's not clear why this is happening. I mean, it's a strongly coupled theory, and yet we have this result as in a weakly coupled one. So this just to show that not everything is understood. I mean, okay, of course, not all of the numbers come out as in experiments. As I said, this 8.4 is close to experiments. It's not exact to any system, but this is a more fundamental puzzle because, you know, whether omega gap is 2EG or not, that seemed like a good test, you know, whether the theory is weakly coupled or not, and there's this case where it doesn't seem to be true. Yeah. Well, yeah, I don't think I want to describe this. This is basically, yeah, this is basically my work, so it doesn't matter. It doesn't matter. It's not so fundamental. There's more specific things, so I will not describe this. So I'll end the lecture here. So questions? Yeah. Just a moment.
So, okay, all this description of this holographic superconductor sounds really nice, really cool, and you have some results that actually match with experiment. But do we actually gain more insight? is there like, because I'm not asking this to sound mean
No,
or anything,
it is a fair question, and the answer is no.
we need to justify, you know, a person that works in condensed matter theory to actually go and learn all this stuff to describe this. So
no, it's a fair question. So in the case of this holographic superconductor, as far as I know, there's nothing new, nothing that people couldn't obtain in other ways. I mean, people have been, so the places where this has mostly been, you know, progress in with respect to usual condensed matter analysis are where people just took general lessons from AdS-CFT and applied them to pure condensed matter models. So that's, for instance, what Sean Hartnell did. He was one of the people, in particular, in the second paper of holographic superconductor, but in many things in these applications to condensed matter. Then he basically kind of switched to doing mostly, condensed matter theory analysis, but with the information that he gained from learning AdS-CFT. So, yeah.
So you would say that the value of using this kind of formalism to describe these systems is more in the insights you might gain from learning these dualities.
Yes,
okay.
And not so much. So not so much in explaining directly some new result which they couldn't explain otherwise, but gaining some insights into how to tackle their condensed matter problems directly in condensed matter theory.
And what about the calculations? Are the calculations made a little bit easier at least, or?
Well, yeah, sure. I mean, that's. I mean, easier. I don't know. For instance, like I don't know how to do numerics. Really, I know just the very basic things. So I couldn't tell you if this is easy. For instance, people have done these things numerically, but I would imagine that yes, it's once you know things, it's probably easier.
All right, thank you.
I've heard of people also using or trying to use AdS-CFT to describe many body systems far from equilibrium, which, strongly coupled far from equilibrium sounds like the most complicated thing you can come up with. So how far along is this line of research? Have we learned new things?
Yeah, again, I don't know if condensed matter theorists would call this new. That's always the question, right? So yes, we have learned new things in that Jesus, I forget the name. Anyway, doing contour integrals in complex time. What's the name? Okay, I can't remember right now.
Real-time formalism, right?
No, not real, not complex. There's the general. How is it called? No, never mind. Keldysh-Swinger formulas. Yeah, so people have been using that for AdS-CFT for a long time, but I'm not sure, and that corresponds to things, to systems that are not conservative. And I'm not sure, not in equilibrium, excuse me. So I'm not sure how much of that could be gained again just in condensed matter theory, because I didn't talk to condensed matter theorists who do this, but to me it seemed new. So yeah. Oh, there's a question here. What do the operators O1 and O2 and their vevs represent physically, and what numerical methods can we use to solve them? Well, so yeah, that what do they represent physically? That's the kind of the point, right? This is a phenomenological model. It's not. So this is in the line of this bottom-up approach, where you just invent a system that has some properties you want, and then try to apply it to the real world. And yeah, it's puzzling. I don't know what. I don't know if there's a system in nature that that corresponds to this, that has two operator vevs and with this particular dependence, because one was proportional to TC, one was TC squared. So they had different dimensions. So yeah, I don't know if there is something that is truly like this in nature. So yeah, I mean, in this case, it's just tells you generically. So this is just some gravity dual for which you do not know the field theory correspondence, right? That's the whole point of the bottom-up approach, that you don't know what field theory it corresponds to. You just know the properties of the field theory. And you're just saying, well, in this field theory, whatever it is, there are two operators of different dimensions, 1 dimension 2, 1 dimension 1, that have symmetry breaking. And yeah, I don't know more than that, what to say.
What about some topological parameters, because they don't obey the Landau symmetry breaking mechanism? Is there any model that describes these topological parameters?
Yeah, it's a good question. Yeah, I am not aware of in AdS-CFT. I cannot swear there aren't, but I'm not aware of. I mean, people have been trying to use string theory in general, string theory methods, but not AdS-CFT, to describe such parameters because of, as you say, they don't vary. So, but yeah, in AdS-CFT specifically, I'm not aware.
Just one more question. In the beginning of the lecture, you defined thermal susceptibility. Is there is that adequate to describe a phase transition as the classical, as the thermal susceptibility in the fields in the condensed matter theory?
Look, I actually don't know well enough the condensed matter part to answer that. What I do know is that there are theorems that say that the susceptibility corresponds to what I define.
Yeah, I was talking about the derivatives that
Yes,
diverge. And
yes.
it's
Yeah.
the same thing.
Yeah, so the fact susceptibility, which you normally would have to do with fluctuations that can be obtained from some sort of more that also correspond to sort of thermodynamic quantities. So these things I don't know exactly how to prove, but they have been proven.
Okay, thank you.
Sure. Well, okay, let's stop here and then have more questions in the question session. I'll see you at 1.